Hello again. Okay. Uh, we're now gonna move on to uh, the continuation of this paper. Okay. And last time in the last clip we solved this model. Okay. Based on the example in the classic paper of Wagner-Witten. Okay. And you have to know that the formulation ignore the I minus variable and also assume that summation ct xt is a constant value. Okay, so but when you apply this, okay, to with uncertain scenario, okay, the model become like this. Okay, equation 7, 8, 9 and inequality 10, 11 and with the integer restriction 12. Okay, when actually they just add one more index on I plus, I minus and D. Okay, the demand is instead of you have D1 to DT, okay, the capital T, okay, you add index S to count the number of possible scenario. Okay, and also the X variable is the same as the first stage variable, and the I plus and I minus is like additional variable to balance the first stage decision to the uncertain condition in the second stage. Okay, and equation 10 is still the same because it doesn't this inequality is just try to make sure that when xt is greater than 0, p sub t is 1. Okay, otherwise 0. Okay, and it's not really depend on the new index s that add to the model. Okay, so we're gonna apply this model. Okay, actually it's pretty close to the regular the variable cost. Okay, but when you add a fixed charge, okay, here of e sub t, okay, here with the p sub t is 0, 1 variable here. This is just an additional with additional constraint 10. Okay, an additional term in the objective function. Okay. And also we have implemented this this model. Okay, using this one. Okay, it's contained in sheet 3 in the file PPC with uncertain demand vendors vs LP. Okay, which you can find in the folder of lecture number 2. Okay, we already explained the sheet number 1. Okay, you remember sheet number 1 we solved this using Excel open solver, and this is the optimal solution, but there's no fixed charge. Okay, in sheet number 2, okay, we illustrate the Bender decomposition, okay, for solving the original problem in sheet 1. In sheet 3 here, okay, we continue to illustrate you the use of Bender decomposition. Okay, we haven't tried to implement this problem to just like sheet number 1 to use the open solver to solve it directly. It would be interesting if you it'd be interesting for you to okay, it'd be interesting if you use the open solver to solve this one, the problem of sheet number 1 when with the additional data here. Let's look at the additional data here. Okay, the additional data is start with column I here in the Excel. Okay, we add a 0, 1. Okay, additional variable here. Okay, this is the current solution, and also the demand it's all the same. The demand is the same. It's 1025 scenario. Okay, it's the same old problem. Okay, with just okay, it's 25, and the balance equation is the same. Okay, but we add this additional variable of 0, 1. Okay, and certainly we need to copy this program, this software to others. Okay, actually we use this order. Okay, to find the I plus and I minus for each scenario. This is the same as usual that we did in the sheet 1. And the cost structure of the I plus I minus is also the same. The cost per unit is also the same. And the nice thing about using the old data here is that with additional of inequality 10 and the term of E sub t, P sub t for summation for all t, it doesn't reflect much for solving the dual problem. Once you already decide the first stage decision, okay. In this case, the first stage decision variable contain x sub t for all t and also p sub t for all t, okay. But p sub t for all t doesn't have any effect on I plus and minus except x sub t, okay. Therefore, when you move this to write in the dual form, okay, once the x sub t and p sub t already initiate, okay, you can find that the sub problem, okay, is exactly the same as in what we did in case when there's no fixed charge, okay. So you can use the old algorithm to identify the optimum y. Okay. Except that the objective function in the Bender cut, okay, down here, you need to add the term summation e sub t et. Or sometimes you can add this summation to the objective function instead of. Okay, and this is almost everything is the same except that, okay, you have this additional cost term, okay, due to the fixed charge, and also you need to add the inequality 10 here to here, because you need to find the new x sub t and p sub t. So the constraint relationship between x sub t and p sub t need also to be identified. Okay, and now we're ready to demonstrate to you that how we can apply or adapt the old methodology to handle this problem in case when fixed charge or set of costs is included. Okay, we go back to the Excel file down here. Okay, you can see that column O and column R are still the same because I already show you that the way to find the optimum dual y is nothing changed. The change will happen in the sub problem here, okay, because we need to have what we call the big M. I'm going to reduce the size a little bit. Okay, let's make it, okay, here. First of all, we identify the big M value, okay. The big M value here is a positive integer value, okay. Now it's around 2000, okay. As I told you before that the value of there's some disruption. Okay, for the 2000 value is you want to make sure that the value allocated for each x sub t, which is here, okay, will not exceed this value. So you might wonder, last time when we solved the previous example we identified 10,000, but this one is only 2,000. Actually, you can have any big positive value as long as you make sure that your x sub t is not greater than this value. Okay, and then you need to add one more changing cell here due to the p sub t here, the 0, 1. No, sorry. Okay, here. The 0, 1 allocation here. And you need to add a constraint that link between p sub t and x sub t, which is here. Which is the constraint is only, you can say that the big M times the 0, 1 constraint minus the corresponding of x sub t, okay. And you want to make sure that this value here over here is an additional constraint need to be greater than or equal to 0. And in this case, our objective function instead we still use the same OT, okay, which is the which is happen to this left hand side and the right hand side, okay. So for the left hand side here, okay, is you need to have this, okay, the cut constraint here, okay, with the left hand side, and this is the right hand side, okay. and we add one more term, okay, of the sum product of p sub t and the constraint here, no, not the p sub t with the setup cost over here, okay, in the line number 2, okay, we import put on the given setup cost value down here, okay, and this is the progress. Okay, we will continue to show you for one more iteration of this. Okay, at this moment, okay, this objective function here, instead of t, you need to add the additional cost of setup cost and the corresponding 0, 1 variable to here to become the objective function. Okay, and but what you have here, okay, you will have this, okay, cut coefficient, okay, with the left hand side and the right hand side. Okay, certainly the left hand side need to be greater than the right hand side, and as you might recall, you remember that your solution down here, so far we start with this solution. Okay, actually you can initiate any solution as long as it is a feasible solution. So what we're gonna do, the thing that we did previously. Okay, so we're gonna shift all the solution, okay, here, okay, just make a copy, and then I'm gonna paste just the value, okay, and then I'm gonna turn all this to have yellow, okay, and certainly the first solution here, okay, I'm gonna move move the current solution that found here, okay, this is a current solution. Okay, I'm going to say copy it, and then I'm going to put it in here. Okay, this is the current solution. Okay, then the new solution that you found in the Bender optimality cut. Okay, sorry. Okay, so this is the current solution. And also we need to move to find a new cut. Okay, we need to move all the coefficients that previously found. Okay, just copy and paste just the value. Okay, and this is very similar to what we did in the Excel's Bender from the previous example. Okay, and okay, the formula is already valid here. Okay, I'm gonna put it in here. Okay, and I'm gonna move. Okay, copy, and then I'm gonna just paste the value. But the first, all the formula are all related to the first constraint, the cut number 1. Okay, it will be updated once. Okay, you put this new x variable here to replace the O1 here. Okay, and certainly once this solution has been you replace it. Okay, all the optimum y will automatically compute it here according to the algorithm proposed by Dr. Pisak, and certainly you're gonna get the new optimality cut constraint. Okay, and certainly your lower bound can be improved. Okay, so now what we're gonna do is that we're gonna try to copy. Okay, we're gonna copy. This current solution, and I'm going to place it here with the transpose, because we have to put it in here. Okay. Once you already put it in here, I think one thing you have to we can utilize the benefit of using Excel, that we can put the formula to give the condition that this value is going to be 0 or 1 when the x of t is greater than 0 here. Okay, this x of t is greater than 0. Okay, and you put 1 here unless you put 0. Okay, so now you already have the new x value. Okay, this new x value. Okay, and also the p sub t value generate the new optimum dual variable, and also generate the new cutting. Okay, cut coefficient for the optimality cut with the left hand side, which certainly always infeasible. You see that the previous one is always feasible. Okay, make sure. Okay, but the new one always infeasible. Therefore, you need to resolve this subproblem again. Okay, and what you expect is that this value will getting increased. The lower bound increase and the upper bound keep decreasing. Okay, actually I didn't store the best solution. One of them you need to store the which one has to keep the best solution over here, expected cost. We're going to keep it as the upper bound. Okay, but this one we are ready to improve our lower bound. Okay, by using we don't need any open solver. We use just the regular solver here. Okay, which I already put all the formula here. Okay, actually the target cell is over here. Okay, the changing cell, okay, will be here, and the value, the allocation value of the x of t and the 0, 1 of p sub t here. So there's two range, U5 to AF5 and U4 to AF4. Okay, here U5 to AF5, here U4 to AF. And also don't forget that you need U1 also, because this is the additional t variable here. So the constraint is here. Constraint, we have to make sure that we put on the new constraint here. Okay, because we already add up one more constraint. Okay, I'm gonna say that. Okay, our constraint is right here. Should be greater than or equal to the right hand side. Okay, I'm gonna add it. Okay, and then we go back to the model again. And also we have constraint that find the relationship between x of t and p sub t is over here. Okay, U3 here. Okay, from U3 to U, this one. Also, I already have the formula here. Okay. Actually, this is the target cell. This is the formula here. Okay, the constraint here. The U3. Okay, all to U3 and like it to all to AF3, okay, have to be greater than or equal to 0. And certainly you need a restriction of this changing cell of U4 to AF4 need to be binary value of 0, 1. So when the model is ready, okay, and you use a simplex LP, okay, to solve this, you can press solve, okay. Take a while, okay. As you can see that, okay, we can run it again. The previous one is 8,174, right? So when you solve it, okay, you solve with the new model with the new optimality cut. Okay, take a while. Okay. There's an improvement for the objective function down here. Okay, and also this one will become feasible solution. So the process keep going on. You add just something like this. You get the new solution here. This you can estimate rounding off this value to become 0 because small one. Okay. Once you already know this, okay, this is a new solution. Okay, you can keep on by replacing this to the new solution here. Move all the solution here. So it becomes the iterative process. You keep going up and down like this, and then try to find whether when will the lower bound reaching the best upper bound that you found so far here. And you can find the optimum solution with those optimality verification. Okay, so that is what we show you, that we can extend, okay, the basic model here, okay, that we solve under deterministic time varying demand. But when you add more scenario to represent the uncertain demand, okay, the same formula can be extended. But what we didn't do is that we didn't try to solve this model directly by using open solver. And I leave that as a homework for you if you are interested to investigate. It might be very efficient. To do that, but we go directly to apply the Bender decomposition to solve this instead of, okay, and just show you under the Excel platform that how can you implement, okay, with additional fixed charge data here and additional constraint here to and using the modify the last vendor approach that we already proposed to you to solve it, and just illustrate to you just one iteration. And actually, if you can write the VBA code, okay, you can implement it and see how many optimality cut that need to be added, okay. And okay, next time we're gonna move on to show you that we can actually solve the problem, okay, the problem in Excel format, okay, by using the MATLAB programming, okay. So from now, okay, I'm gonna stop this session and see you in the next session. Okay, see you all.